Hello, pre-calculus students. This is Mrs. Leopold, and today I am going to talk about Unit 4, Lesson 5, which is all about inverse trigonometric functions. This is a new lesson this year, 2021. We have not previously taught inverse trigonometric functions in pre-calculus, so you will not see any questions on former quizzes or in former notes packets. This is the first time we've taught it in quite some time. So let's check out our lesson objectives. Our lesson objectives are we're going to graph the inverse trigonometric functions for sine, cosine, and tangent. We're going to analyze the domain and range of inverse trigonometric functions, and we're going to solve equations using inverse trigonometric functions. Okay, but before we do that, we are going to look at some definitions. So the first definition, there's also a warm-up, but I'm not going to talk about the warm-up. It's just on your graphing. So you can go look at the answer key if you did the warm-up. You should definitely do it to practice, but I'm not going to discuss it here. All right, back to our definitions. So the first definition here is about a one-to-one function. So a one-to-one function, you talked about this in Algebra 2 Trig. We talked about it extensively when we did our quadratics unit. But a one-to-one function is a function that is one-to-one, which means if for each x coordinate, there corresponds exactly one y value, and for each y, there corresponds exactly one x. The quick and easy, graphic way of determining if a function is one-to-one was using the horizontal line test. One of the functions we studied quite a bit last year was your quadratic, right? So if this is your x-axis, your y-axis, we graph our quadratic function, looks something like this. And then we talked about how the fact that it fails the horizontal line test, it passes the vertical line test, so it is a function. However, it fails the horizontal line test, which means the function is not one-to-one, right? So this horizontal line right here, it intersects the quadratic function in two places, therefore it is not a one-to-one function. Now, we could make it a one-to-one function if we chose either the right-hand side or the left-hand side. So if we chose just one side of that quadratic, and we said, you know what, we're only going to look at that quadratic if x is greater than or equal to 0. So we're only going to look at this side. So I can erase the other side here. Oops, I guess I can't do that. Then I'm going to graph that inverse. So the inverse is then just the square root of x. So I'm only taking the positive portion. So that would be just this red graph right here. Right? So we would have this original blue graph, just this part, and then its inverse if we wanted to make it one-to-one. We would get rid of all the left-hand side, only talk about the right-hand side, and now that function would be one-to-one. Now, if that function was one-to-one, because I limited the domain, then you will notice that it is also monotonic. So what is monotonic? It says a function is monotonic if it is always increasing or always decreasing on its domain. So if I limit my domain to x is greater than or equal to 0, then this original function, blue function here, part of the quadratic is always increasing, and then if I did the square root function, that is always increasing as well. So that is also monotonic, and they're one-to-one, so therefore they are inverses of each other, right? So what is an inverse? An inverse means that it's going to be monotonic and one-to-one, and when something is an inverse, notice that I had already used that notation up here, so f to the negative 1 of x is the inverse notation. Another thing that we talked about in Algebra 2 Trig was that if g of f of x equals f of g of x, and both of those equal x, then that also proves that something is an inverse. Now, why is that? Right, if you plug in an x value for f of x, you end up with the y value. And whatever that y value is, this whole thing becomes the y value. And when you take g of that y value and get back the x value, that means they are inverses, because inverses just switch your x and y coordinate, or they are reflective over the y equals x line. So that's also something we learned about inverses, is graphically, if we have a line going through here, right, they reflect over that line, and those are inverses. So the x becomes y, and the y becomes x. So this statement, f of g of x equals g of f of x equals x, is just saying, hey, if I plug in an x, I get a y. Take that y value, plug it back into the other function and get an x, then that means the x and y coordinates just switched. So they are inverses of each other. Whew, that was a lot just about the definitions. Okay, this next part, the inverse sine graph. You should just be able to do this on your own. You can pause, go through all of this on your own, try to answer the questions, at least part 1 through 4. And then you can come back to me when you are done. So I'm going to pause as well and do a little bit of work on my own. Okay, so your curve is just the basic sine graph. So it should look something like mine up here. It starts at, well, we think of this as kind of at 0 at the origin. It's going through the origin, then it goes up to 1, then down to 0, then down to -1, then back up to 0, and then going the opposite direction. We have those 4 points there. So is this function one-to-one? Well, no, you can see it's going to fail the horizontal line test, right? If I drew a horizontal line, it's going to fail the horizontal line test. Is this function monotonic, number 2, on the given interval? No, from -2 pi to 2 pi it's not, because it's increasing here and then it's decreasing here. So monotonic means it either increases the entire time or decreases the entire time. Is the inverse of this a function? No, it's not, because if the this graph is not one-to-one, then its inverse is not going to be a function. So now we're going to the next part, which says restrict the domain so that the graph is a one-to-one function. This can be done on many different intervals, so you have to use these following 2 conditions. Number 1, the angles must be included in the first quadrant, so you have to include those. And then number 2 is you need to make the restriction as large as you possibly can. Okay, so if we're thinking about our angles in the first quadrant, remember you have, this is your quadrant 1, quadrant 1, 2, 3, and 4. So these angles here are between 0 and pi over 2. So we're talking about these angles up here. So these angles between 0 and pi over 2 need to be included. So this part of the graph has to be included because that's between 0 and pi over 2. Now, if we wanted to pass the horizontal line test, then we certainly cannot continue going down through here because it would not pass the horizontal line test. So instead, and I also need to make sure the restrictions are as large as possible. So instead, I'm going to go back the other direction. I'm going to go down to the 4th quadrant. So I'm really looking at the first quadrant here, but I'm also looking back here into the 4th quadrant. And when I go backwards, right, I'm looking at a restriction that's going from negative pi over 2 to pi over 2, right? So I can't go this direction and include these values between 3 pi over 2 and 4 pi because that's not, I have all this part in between that I'm not using. So I have to go backwards and look at my, restrict the domain to make it a one-to-one function to just go from negative pi over 2 to pi over 2, and this would be the part of the sine curve that we would restrict that we're going to use for the inverse sine graph. Okay, so we're going to now sketch the sine graph on this new domain. So I just rewrote it on this slide. So our domain is now from negative pi over 2 to pi over 2. And so when we do that, you'll notice that then our graph would be one-to-one, and it would also be monotonic. So we start the cosine curve, or usually goes to the origin, then as we go to pi over 2, it goes up to 1, and we go to negative pi over 2, it goes down to -1, and it would have kind of a bit of a curve. It's a little hard to show that curve, but you want to make sure it doesn't look linear. A little more of a curve can be something like that. So that is the sine curve with that limited domain of this. Now, you can pause and try the next part on your own. It says sketch the inverse of number 6 on the graph below. So I think on your notes this year, in 2021, I think we messed up this graph. Notice the x-axis should have numbers on it from -1 to 1, and the y-axis should be your angle measures of pi over 2, pi, etc., because we're reversing the x and y ordered pairs, right? That's what inverses do. They take the original ordered pair, reflect it over the y equals x line, so then the x becomes y and the y becomes x. So that means my axes have to change their measurements as well. So I see I have this 0, 0. Actually, I'm going to use a different color. It's going to go through 0, 0 still, but here I went to the right pi over 2 and up 1. So the ordered pair was pi over 2, 1. So down below, I'm going to go to the right 1, up pi over 2. And then here I went left pi over 2, down 1. Right, so when I switch that ordered pair, it's going to be -1, negative pi over 2. So I go to the left 1 and I go to down negative pi over 2. And so my graph looks something like this. Now, how should it curve? That's the question. So it should be curving up and down a little bit, something like that. So this graph right here is the inverse sine graph. Right, so this is the inverse sine graph right here in red. Okay, now let's talk through all of these different little boxes here and read through and try to discuss what it means, although I'm just talking to myself, but hopefully you can follow along. It says the equation of the inverse sine function. The equation for the sine function is y equals sine x. Recall that the equation of an inverse, remember we already talked about it, is when you switch x and y for x. So the ordered pair just switches to those opposites like that, yx, xy. So use this knowledge to create an equation for the inverse. Well, if this was the original, then what are we going to do? We're going to switch the x, we're going to switch the x and the y. So it becomes x equals sine of y. So x is, okay, so it says the equation in number 1 is written such that we need to solve for x by using y. The following sentence represents the equation you wrote in number 1. Well, it's y. What is y representing? This is representing now the angle, right? Y is now the angle instead of x being the angle. So y is the angle whose sine is x. So x is your ratio, your trig ratio, and y is the angle measure now because we've switched our x and our y. Okay, well, instead of an angle measure, we often, now our language is about radians. So remember that radian measure is just arc length divided by radius. And in a unit circle, a radius has a length of 1. So therefore, the angle measure would equal just s, or just the arc length, right? So if theta equals the arc length, then angle can also mean arc. And so when you put number 2 and number 3 together, instead of y is the angle whose sine is x, we can say y is the arc whose sine is x. Or that is where you will now see you can use arc sine to indicate that you are taking the inverse. So y equals arc sine of x. Okay, so let's just summarize all this all together. You should pause and try this on your own, right? Go ahead and pause, try to identify what is the domain of the arc sine x, what is the range, what does that graph look like again if you want to repeat it, and then we'll talk, I'll do it myself as well. Okay, so do you have the graph again, right? So this is what your graph should look like here on the right-hand side. And then what is our domain? Well, you can see our domain goes from -1 to 1, both inclusive, so I have my square brackets there. And then I went down from -pi over 2 to pi over 2. So again, inclusive of those because we do have points here and here. And what does y represent in this case? Y represents, so what is this representing? It's representing the angle measure in radians, right? It's representing the angle measure in radians. Notice we could use the words arc sine, or we could use sine to the -1 of x. This is interesting. You should go ahead and use your calculator to graph. What do you think is going to happen when you grab your calculator and graph y equals sine to the negative 1 of x? If you haven't tried it, you should try it. See what happens. All right, here's some practice problems. These are types of problems that you might have on your assessment. So it says evaluate, and this would be on the non-calculator portion, obviously, because it says no calculators. So how would we evaluate these? Well, because they're all dealing with arc sines, the first thing you need to remember is that we have a domain restriction for our arc sine and a range restriction for our arc sine. And remember, when it says arc sine, it's asking for the angle measure, right? We just talked about this is y equals arc sine, so y is representing the angle measure in radians. So remember that we have a restriction from negative pi over 2 to pi over 2. Well, you might want to just think of that with your unit circle, right? So if we're looking at pi over 2, negative pi over 2 to pi over 2, we're looking from here in quadrants 1 and quadrant 4, right? So we're looking in quadrant 1 and we're looking in quadrant 4. So that will just help us really quickly. If you want the angle measure that would produce sine of a value of 1/2, well, hopefully you're saying to yourself that would be pi over 6. Because this is a positive 1/2, then we're talking about values in the first quadrant. So that would just be equal to the radian measure, the rotation of pi over 6 units. Arc sine of 1 over root 2. Again, it's a positive number right here, which means we're talking about an angle measure in the first quadrant, because all trigonometric angle measures are positive in the first quadrant, or all all trigonometric ratios are positive in the first quadrant. So this would just produce an angle rotation of pi over 4. Now for our third example, we want a negative value. And if we want a negative value, remember sine is negative in the fourth quadrant, so we're actually going to be doing a backwards rotation. So negative root 3 over 2, well, root 3 over 2 produces an angle measure of pi over 3, but because it's in the fourth quadrant and it has to be restricted in this domain, it's going to be negative pi over 3. And finally, this last problem, notice this is a composition here, so we have to start with the parentheses. So what is arc sine of 1? So arc sine of 1, well, in between, the only point that's going to potentially have a 1 is this point here. Arc sine, we have this point up here, which is 0, 1, and we have this point down here, which is 0, negative 1. So sine is associated with the y value, so when is the y value equal to a positive 1? Well, that's at pi over 2. So this whole thing right here becomes pi over 2, because that's the angle measure that represents arc sine of 1. So now we're actually calculating cosine of pi over 2, and cosine of pi over 2, you can see with that ordered pair here, is just 0. This domain, I don't know what just happened. Here are some questions that you are going to calculate using your calculator. So if you don't have your calculator, I would pause and go grab it. Notice this time we're actually trying to find all possible angle measures that are caught between 0 and 2 pi, right? So all solutions that are caught between 0 and 2 pi. So I want you to try this on your own for a moment, and then you can unpause when you're ready to check and see how you did compared to mine. Okay, did you get these answers? Did you get 0.412 and 2.730 for number 5? Hopefully you remember that there are 2 answers, right? This is just saying when will sine of some angle measure equal 0.4? And that's asking again for all the solutions between 0 and 2 pi. So if you're thinking of that graphically, here's the sine curve between 0 and 2 pi. So when will the sine curve equal to 0.4? So that's going to be here and here. So those are my 2 angle measures that are going to equal 0.4. And so I have 2 answers. One is in the first quadrant, I can see here, and the second one in the second quadrant. So there we go. The second example is the same. So it says 1 is sine of x going to equal negative 2/3. Again, here's my sine curve. So I have negative 2/3, so I'm going to have two locations where that's going to happen. That's going to happen here in my third quadrant and my fourth quadrant. So when I plug that into my calculator, I get a negative 0.7297, but that's not in the domain restriction. So I have to alter that to make it in the domain restriction. So I can rotate this direction, which means pi plus that value, which was 3.871, or I can go to my fourth quadrant and I could do 2 pi minus that value, and I got 5.553. So that's for number 5, number 6. And number 7, they just said, what is the arc sine of 1? So it's asking the angle measure that would produce a numerical value of 1. So in this case, you just have one simple answer. It's going back to our inverse trig, and our answer is, it's restricted on this domain right here. So here we have it, and we are done. All right, this one, tricky. Let's see if you can do this without a calculator. I would encourage you to try to do this on your own. It says include the domain and range. You're trying to graph now some changes, right? What are we going to do with the 2 in front of the arc sine, a 3 paired with the x? What would you do? Okay, let's think about what our original domain is. Our original domain was caught between negative 1 and 1. Our original range was caught between negative pi over 2 and pi over 2. Now, why am I doing this? Well, if you look at this right here, what if I rewrote it as something like this? So I can see here with my x, instead of having an x here, I have a 3x. So now I can divide everything by 3, and I can see my new domain is x, caught in between 1/3 and negative 1/3. So this is my new domain. And my range, well, I moved that 2 to the other side. So now instead of having y in here, it's y divided by 2. So I can multiply everything by 2. So now my new range is caught between negative pi and pi. I'm going to leave you with that. Have a look at what we did there to figure out what our new domain and range is. I want you to pause, and I want you to try to graph this new inverse trig equation. Okay, is this what you got? Instead of having negative pi over 2, negative 1, negative pi over 2, we have negative 1/3 and negative pi, and then it goes through 0, 0. Instead of having 1 and pi over 2, it is now 1/3 and pi. So this is what you should have. So again, look at what we did here with these values to find our domain and range, and look how much easier that was to then graph with those transformations. All right, we've explored the inverse sine function. So now let's explore the inverse cosine. So graph the cosine curve on the interval from 0 to pi. And what do you notice? Well, you should notice that the function is monotonic. It's 1 to 1. So your cosine curve starts at 0, 1. It goes through 0 at pi over 2. And then it goes through pi negative 1. So it curves something like that. So that would be what your cosine curve would be, and that passes the 1-to-1 test. It is monotonic, it decreases the whole time. So this is going to be what your inverse is connected to. So here I regraphed it on this page so you can see it. Now what are you going to do? I want you to take some key points. I want you to reverse the x and the y coordinate so we can graph the arc cosine, and pause and try that on your own. So do you have it looking like this? The domain is now, you can see, restricted between negative 1 and 1, which makes sense because that was my original range. And the range is now restricted between 0 and pi. Again, that makes sense because that was my original domain. So inclusive on all of these, you should have something looking like this. Now try your arctan, the last function. So I would pause, try it on your own, and see how you do. Okay, this is it. Did you get a graph that looks like this? Hopefully you did. At pi over 4, the tangent function's at 1. At negative pi over 4, it's at negative 1. But now we reverse those x and y coordinates, the x and y axes, so it looks like this. Again, if you have questions, please reach out to your teachers. We are here to help you. It's hard for me to explain everything via video, and there's no questions that I'm answering to further help you along. So reach out. We're happy to help. Bye.